Let's continue with BFS traversal. So we are looking at this second application, which is checking bipartiteness. Can you partition the vertices into A and B such that A and B are, they don't have edges inside, but all the edges are cross edges, A cross B edges. So this is a hard problem by definition. Okay, but using BFS and some graph theory, we can actually solve it very fast, as fast as BFS. So for that, we have to understand few more things in BFS, what happens here. So BFS actually gives a tree, so the graph has red and blue edges, but the red edges are the ones which BFS followed and updated the D array and got the correct distance from X. BFS started on X. So you get these ripples, so V0, V1, V2, V3, V4, dot dot. It will go up to Vn minus 1. And so red edges form a tree. Is that clear? Why can't there be a cycle in these red edges? Yeah, so that is by the pseudocode of BFS. You read the pseudocode of BFS, you will see that the red edge can never go back because red edge is by definition the first update. So it only goes to a unvisited vertex. If there was a cycle, then it would be saying that red edge is going to a visited vertex, which is a contradiction to the pseudocode. So that's the tree with the red edges. Okay, so that is the definition of the tree T. And but there are more edges. Graph had more edges, which we have kind of ignored. So these are the blue ones. So let's look at a vertex W, which is in Vi, ripple Vi. And so what kind of edges can go out which are blue? Right. So we have observed quickly that from W you cannot actually go to Vi minus 2. Because if you went there, then this would contradict the distance of W. And similarly, you cannot go from W to Vi plus 2. Okay, so the only possibilities are either in Vi or Vi plus minus 1. So these are this completely describes the graph under BFS or after BFS. So the non-tree edges from Vi go to Vi minus 1, Vi and Vi plus 1 and nowhere else. Okay, this is an important observation of the BFS tree, which you use in many algorithms. So now let us complete idea 1, what to do with this tree to detect bipartiteness. So we'll just, kind of without loss of generality, we will label A and B already. So A is the odd ripples, the even ripples, and B is the odd ones. Okay, because there is an edge from V0 to V1, so which means that they can only have opposite belongings. So either you put V0 in A and then V1 goes to B. right? So that is the candidate partition of the vertices given by the ripples, even ripples versus odd ripples. Now to complete this pseudocode, what you have to now see is whether this actually works, which means that is A H free and is B H free, right? So when is A H free? Like you see in Vi or V2, A is not H free because there is this blue edge, right? So this A will actually not work. So when it doesn't work, can you now output that graph is non-bipartite? Right? That was the hard case. That was the thing to prove. So why is it? Why can you output? This is just one possibility of AB, right? From one possibility, how are you claiming that there is no possibility of partitioning into AB? So this blue edge is actually giving you a cycle of size 5. Right, it's 2 plus 1 plus 2. So from X, you are actually getting a cycle, which is of size 5. Now, if you have a cycle of size 5, can such a graph be bipartite? It cannot be, right? You just saw an example. You saw this observation that odd cycle is non-bipartite. So if a non-bipartite thing is sitting inside a bipartite, well, if this cycle, for example, is sitting in a graph, then the graph cannot be bipartite, because bipartite graphs have only even cycles. So because of all that, you can immediately say that there is no possibility at all. So that is what you are checking. So you alternate or just define A to be even ripples and B to be odd ripples, and then you check that if there exists an edge in any of the VIs, then this gives you an odd cycle involving X. Which implies that this graph is non-bipartite. And if there does not exist any edge, within Vi for all I, then it means that, yeah, so then what you are saying is that within no level Vi is there a blue edge, but there can still be blue edges from Vi to Vi plus minus 1. So Vi plus minus 1, right? That is the situation you are at. There is no edge Vi to Vi, but there are possibly edges, blue edges from Vi to Vi plus minus 1. But they are fine because they are actually changing parity, right? They are going from, in this example, A to B. which is anyways allowed in bipartite graph. So what you can deduce now is that the graph is bipartite. So then V equal to A disjoint union B works, and G is bipartite. Okay? Is the pseudocode clear? So based on this, you can just write the pseudocode, just adapt BFS pseudocode. Any questions? So how much time will this take? Yeah, so on top of the BFS pseudocode, what else are we doing? I mean, once you have all the complete BFS, you have the D array. So you just have to iterate over all the edges. And when you go over the edges, you look at the endpoints of an edge, UV, and just check the D values. Right? If for any edge the D values of the endpoints are equal, then that's this bad blue edge. And if that doesn't happen, then it's a bipartite graph. So it has become, this very hard problem has completely become trivial now after BFS. So bipartite representation can be found in order m plus n time. Right, this in fact was one of the reasons why BFS was invented, to solve this hard problem. But obviously BFS can do more than just this. Any questions? No. This is just the pictorial representation. The pseudocode of BFS will already give you a D array. So apart from the D array, you don't need to store anything else. No, but BFS algorithm just outputs a D array. There is no tree, no edge, no such thing is recorded or outputted. So the D array just tells the distances from X. That's all you need. Because once you have the D array, then given any pair of vertices U, V, and basically the edge U comma V, you can find out whether it's a blue edge or a red edge. Because that is what we have learned here. So this an edge UV is blue if and only if in the D value is this well, let me say is blue inside Vi if and only if D of U, D of V is equal to I. So this, the picture is actually completely implied from the D array. You don't need to store this picture. So somebody gives you U comma V, you can just look at the D array and in constant time you know whether it's a bad blue. So bad blue is the blue edge within a layer like Vi. And the good blues are going across, that we anyways don't care. That's not a test we need to do. So which is why this is as fast as BFS. You don't need to do much. You just have to add this one line and iterate over all the edges. A for loop on the edges. Okay. So if BFS is done, then we'll move on. So what is the opposite of BFS traversal? Yeah, so the opposite of BFS traversal is DFS, which is depth first search. Okay, so the difference is like half of you students have the BFS personality, which is that you try to learn as many areas as possible without knowing much about anything. And the other half have the personality that you are DFS, so you learn only one area, but you learn everything that exists in human understanding. Okay, so BFS is the first type. DFS is the opposite, where you just do one area, but you do it as deep as possible. So now we'll do that. So DFS will turn out to be far more powerful than BFS. Okay, DFS is a more popular traversal of graphs. So let us formalize that. So what is done here is that instead of the ripple, which is looking at only distance I vertices, now you will start from X and you will keep on picking a neighbor and neighbor of that and so on, and keep on moving as deep as possible, okay, without worrying about increasing distances. So here the basic idea is that keep moving to the neighbor of neighbor and so on, okay, till you repeat. And during this process, you keep remembering the timestamps. So like so you start from X, so that is 0 second, then in the first second you will pick one neighbor, and in the second second you will pick neighbor of that, and in third second you will pick neighbor of neighbor and so on. So you keep time stamping, and obviously when you reach a place where you had already visited, then at that point you abort. So you basically trace back. So tracing back means that let's say you went to a neighbor from X, you took this route, and then you took this route, and then suppose you get to see this edge, right? So but X was something you have already visited, so which means that at this point you have to change a previous choice. So you backtrack. So maybe there is a neighbor here. Okay, so when you got into the cycle, you backtrack and you come here. From here you come to the previous vertex and pick a second neighbor, which is this one. Okay, and then you continue deeper on this side, till you again hit a repetition. At that point, you will just take one step back and see whether there is a new part to explore. Okay, so you pick a new part to explore only when you have discovered everything that was to be discovered in previous choices that you made. Okay, so this is a very different strategy than BFS, than doing it breadth first. How do you think that you will implement this? Yeah, so this is recursion. So you just pick a neighbor and you do DFS recursively on that. But you also have to maintain visited vertices, so you maintain a flag. So that you know that in the recursion tree exploration, when you reach a vertex which is already visited, then it means that now is the time to backtrack and pick something which is unvisited. So the green one is the backtracking. Okay, so you backtrack, and these orange ones are basically becoming red edges. Right? These are the interesting paths which you, or edges which you took to get new or unvisited vertices. So this will also give you a DFS tree. So that is what we have to now explore. So this is a very powerful graph algorithm. So this is a very powerful algorithm in computer science. It has lots of applications, some of which you will see in the class, and the others you will see in the exams. Okay, so it's not always easy to connect DFS with the problem at hand, okay, because DFS has tons of properties. So you have to be quite experienced in this. So this was invented by a famous computer scientist, so Robert E. Tarjan, in 72. Okay, but instead of calling this Tarjan's algorithm, we just call it DFS. And DFS has many versions, so I will just do a simple version in the class, but if you search online, you will get other versions which are better for other problems. So yeah, so we can actually give the pseudocode directly. So let's look at the pseudocode of this using a recursion as suggested. So you want to DFS traverse a graph G. So what you will do is, what is given here is so G has V comma E, and there is an array that we maintain which is DFN array. So DFN array will just timestamp. Okay, so the time starts from 0, and then as you move forward, the time increments. So DFN array is just depth first number. So this timestamp will ultimately label all the vertices with the seconds at the time when you reach that vertex. And then there is the visit flag. So, and I think I also need a global variable for the time stamping. So there is this variable DFN. Okay, so this is what the graph will contain, and then as we are making recursive calls, we are actually sending all this information. Okay, this will be global to all the recursive calls. Okay, so you start with initializing DFN 0. And for all the vertices, you initialize them unvisited. And for now, after, so this is the initialization phase. After this comes the main for loop where you will try to visit connected components essentially. So for a V, you check whether V is unvisited. If it is still unvisited, then you do a DFS call, recursive call. I mean, we have to write down this function DFS G comma V, it will be a recursive function. So that's the first, that is the main subroutine, and the DFS is now what we have to do. Okay, so what DFS? So DFS will be the main engine. DFS traverse is just the subroutine that will call this main engine. So in DFS GV, this will be recursive. So what it will do is, this is the first time you are actually visiting V. So you set it to true. The purpose of this is to traverse from V. Okay, so small v is unvisited, and you will basically visit everything which is possible in the depths below V. So you first set visit V to true, and you set the timestamp at the current level, which is, so you set it to the current time and increment. Okay, so the timestamp will be given to V, and it will be incremented for the next vertex. And for all the neighbors of V, which are unvisited, what should you do? Recursive call, right? So visit. So now do DFS on W. So that's it. So you just call V visited, set the timestamp, and then go to the neighbors and one by one do recursive call, if the neighbor is unvisited. Okay, so this exactly implements the picture. So it will, from X it starts and it goes down, and when it hits a visited vertex, then it has to backtrack. Is that clear? DFN is a unique number which will be given to every vertex. It's from 0 to n minus 1 exactly. So the vertices are n many, and they will be now labeled 0 to n minus 1 in a unique way, in a distinct way. It's the timestamp. It is the, see, this computer is still a sequential machine. It is not doing things in parallel. So the computer has its time clock, and in that time clock, whatever vertex it will see, it will give it that time. So 0 to n minus 1. Which is why I said that DFN is small DFN is a global variable. So any recursive call will update it once, and then the next call will update it, and so on. It's the time on a sequential machine, which your computer is anyways. So the pseudocode is easy enough, right? But its implications are quite complicated. So now let us see that maybe in an example. So let us start from 0, that is your root. Maybe I draw let's do it differently. So first let's draw the graph. Okay, now let us put the numbers. So this is 0. This vertex, let's call it V. You are doing DFS G comma V. V is the root. So the timestamp this has is initialized to 0, and then so this has many neighbors, right? It has 5 neighbors. So based on some magic, one neighbor will be picked, unvisited. Let's say it is this one. So now this will become timestamp 1, right? This is DFN, value is 1 here. Then again 3 neighbors. So by magic this one is picked. So you go to that. And now what happens? So when you go to 3, whatever neighbor is picked, you will see that you are repeating, right? So that this gets discovered, let's say, here. Okay, so 3 neighbor 0 is picked, and then it is seen that by the DFS subroutine it is seen that this is actually a repetition. So you have to backtrack. So when you backtrack, you will go where? So now, yeah, now this 2's neighbor will be explored. Something which is not yet seen. So let's say by magic this is picked. So I'm saying B for a back edge. Okay, so 3 to 0 you wanted to take, but that's a repetition. So you backtrack. So backtracking will take you from 3 to 2 because that was the path you took. So you go to the nearest one before. So you go to 2. And then you, by magic, you will pick this next unvisited vertex, which you will call what? 4, right? So we'll not count backtracking. So this will be 4. And then there is a unique choice here. And here 6. Now when you reach 6, I should have drawn one more edge. There was this edge. So when you reach 6, then you will want to take this edge, but then you will see that it's that this is a repetition. So you have to backtrack. So when you backtrack, you go where? You go 5, but that again will take you to 2. That again is calling for a backtracking. So from 5 you go where? 4. From 4 to 2, and from 2 to 1 to 0, right? So the backtracking backtracks all the way to the root. And then what do you do? Yeah, so then again by magic you will pick one of the 2. So let us say you pick this one. And you put what label? 7. And then you put 8 here. And then this one is backtracking. Okay, so that is what is DFS. Okay, so you had 9 vertices and it has numbered them 0 to 8. But there is a deep structure it has discovered which will unfold over the lectures and over your exams. Okay, so you have this, first of all, the red edges are giving you a tree that's called the DFS tree. And in this class we will characterize these back edges. What is their property? It forces a backtracking in recursion. Okay. Okay, so some quick observations we can make. So DFS V calls DFS W. Let us say. So just by the properties of recursions, you can say that which one of these will finish first. It's a subroutine, it's a function call. Which function finishes first? DFS W will finish first, right? Because it's a recursive call. So basically the exploration of W happens and only then V will continue the next call, right? So that's one thing to remember. So DFS W, it implies that DFS W finishes before DFS V. That is simply how recursion works. And the other observation is that DFS U on some vertex U, DFS U is executed only on the unvisited vertices. Okay, this again is how the pseudocode is. Just by the pseudocode's if statement, if visit W, if W is already visited, then it will not be explored. Right? So DFS U is executed only on unvisited vertices. So these are the simple observations from the pseudocode. And so based on this picture that you have now, let's state the main DFS theorem. So DFS GV visits each vertex in the connected component of V in that graph. Okay, so once DFS starts on V, it will not stop till it has covered the whole connected component. And remember, we are only in undirected graph, right? This traversals we are doing for undirected, which should be set somewhere. It's an undirected graph we are talking about. So connected component is a natural thing, and the whole of that will be covered. That's the first claim. That's the first theorem you get, and the second property is the time complexity. So DFS traverse on the graph G, this pseudocode, it visits all of V, connected or not, and takes time. Yeah, again m plus n, you don't want anything more than linear. So these are the strong properties. So how do you prove the first thing? The DFS on V visits the whole connected component. Sorry, the second answer was? Yes, so you are, when you are backtracking, you are not going outside the connected component, because you backtrack to the nearest one in the path that you have taken, and from there you just will move to a neighbor which is unvisited, right? So at no point of time are you moving out of that connected component, and you will keep on exploring till everything is explored, because if there is a vertex in the connected component which you have, which is unvisited, so I mean technically it's a proof by induction. So that let's assume that some vertex u is unvisited and DFS on V has stopped. So then you should look at the connected component minus the vertex u, and there you will see that since by induction that whole thing is visited, so there is a vertex there which is a neighbor of u. So when the DFS reached that vertex, it should have covered u also, right? So by induction you can prove this. So you just have to observe that DFS of V calls DFS of W which will run on a smaller graph. Right, so this is a call for induction. So inductively you can assume that DFS W will work correctly. It will cover the whole connected component of W. And from there you can deduce that it will cover, ultimately the connected component of V also will be covered. So by induction on the graph size, deduce that the connected component of V is visited. Is visited completely. Okay, so just complete the induction, complete this deduction, inducting on the size of the subgraph. And obviously the base case of the induction is trivial. Base case is just there are one or two vertices in the graph. There is just single edge. So if there is a single edge, then obviously DFS covers the whole single edge. Right, so base case is trivial, and induction step is this. So that will give you that everything in the connected component of V is covered, is visited. And next is the time complexity. How do you show that? Yeah, so each edge is, yeah, so that is the most important observation, that so the well, an edge is seen at most twice, right? So I mean, one is the first time it is seen, it's actually a red edge, becomes a red edge in the DFS tree. And in fact, I think second time there will be no opportunity for that. So second time you can say it was just the backtracking which happened. Yeah, so no edge is actually seen more than twice by the pseudocode. As the pseudocode runs across all recursive calls, across everything, from time 0 to n minus 1, one edge E is covered only twice, right? So, and also conversely, in your all these executions, this is actually only seeing an edge. It is just traversing an edge. So every step traverses an edge, and every edge is visited at most twice, right? So from here you get number of steps. Is following an edge. And any edge E is used at most twice. Okay, so this is from the picture, from the pseudocode. This is one thing, and then you have to see how much data is being stored. So the data storage is, you are storing the graph, you are storing the DFN array and the visit array, which are of size n. Right? So it is order n for the array storage plus number of edges. So that gives you n plus m. This implies that time is, or number of steps is n plus m. Is that clear? So just understand the pseudocode and then see the proofs of this. Okay, so once this is done, then we have to understand more about these back edges. Okay, what are these back edges signifying about the graph? So let us study the DFS tree. So some of the properties of this tree is, let's call this T. So the first property is that this DFS tree is not unique. Given the graph G. For a graph G, this is not unique. Why is that? Yeah, so I told you that these red edges are being picked by some magic, right? So in the very first step, when you went from 0 to 1, that was arbitrary. There were 5 neighbors. Any of those could have been picked. So how is this being decided? Yeah, so this actually depends on how this adjacency list which represents the graph was given in the input. So if the user gave neighbor 1 the most priority, then that is what you will see first. But if somebody else gives 7 more priority, then 7 will be seen first, so 7 will become 1. Right? So the tree will completely change. Why will it change? Because you will go from 0 to 7, 7 to 8, and then after that you may take 0 to 3. So a different kind of red edge will appear, which is in this picture a back edge. Right? So these back edge red edges are not they are not canonical. They change with the input representation of the graph. And they change on how you are picking it, what magic you are doing. So these things are not unique. And second more interesting property is, which we'll prove to, next time, that non-tree edges, which is the back edges, that is x comma y which is an edge in the graph, but it is not an edge in the tree. Okay, so these non-tree edges these satisfy the following property, which is that X is an ancestor of Y or vice versa. Okay, so they satisfy this ancestor descendant property in the tree. Okay, so in the tree, when these back edges, again in the picture, when you see back edge 3 to 0, you can clearly see that 3 is a descendant of 0 in the red tree. Right? So that is a property that you can show, that will show next time, that these back edges are actually just pointing to an ancestor in the tree. So it is not the case that the picture is like this. That X is here and Y is here, and then there is an edge here. So this is not what is happening. Okay, so back edges are not of this type. It's not that in the tree, the left and right children, there is an edge, because this won't be ancestral.